Hello, I'm Scott Harris from the Colorado School Minds, and I'm going to talk to you about a pool table recognition algorithm I developed. First, just to go over the goals of this algorithm, I wanted to be able to find the balls in play, then create a top-down map of the table, and to do this I wanted to use multiple views and of the table, and as a secondary goal, classify the balls as either stripes or solids. So developing this algorithm used a few topics of computer vision. These include circle finding, projective transforms, and just general image statistics. So a lot of my classmates also developed pool table recognition algorithms, and there are just so many circle finding algorithms out there. But as far as pool table mapping systems, a lot use just the full table, a full view of the table. So that means you have to have the picture from pretty far away or from weird angles. And most of the things out on the market right now require you to have additional equipment just looking down at the table from the top. So to do this, I made some assumptions. First, we were going to use a standard pool table, which is just brown wood on the outside with the green felt on the inside. All pool tables have markers along the bumpers, and we're assuming that the particular table we're using has circular bumpers. We have to take 4 images at each of the corners, and they have to be taken in a specific order. As you can see here, this is what we want the sequence of images to look like. So we want to start in the bottom right corner of this image and move counterclockwise around, taking a picture at each of the corners of the table. Doesn't particularly matter that you start in the bottom right, but you need to start at the short edge of the table and then move to the other short edge and then flip to the other side. So the algorithm can pretty much be split into 2 steps. We're going to be finding the balls, and then we're going to be mapping the table. So to find the balls, we're assuming we're looking for balls in that specific corner of the image, so we're not going to look for a really large range of radiuses for the balls. We're going to look for light and dark polarity because some of the balls are darker colored than the felt and some are lighter colored. And then we're going to just eliminate any false and double detections we have. So this is an example of just the first run through of circle finding on the image. You can see that a lot of the balls are found twice. And we get rid of that by just taking the or looking at the centers of all the found circles, and if one center is too close to another, we just ignore that one. And we are taking the centers from the light polarity search, trump ones from the dark polarity search. And that's just because you can see here that the shadow of the ball is detected a lot. So this is cleaned up after we go through the center removal part of the program. You can see everything's pretty clean right now. Still, this one false detection of a shadow got through. So next we wanted to try and classify the balls as either stripes or solids, and the way we're going to do that is by using the standard deviation. So solids inherently have fewer instances of color, and that's pretty obvious if you think about it. So the striped balls have white patches and then a colored patch and then a white patch. So it's my thinking that a solid ball would have a lower standard deviation of pixel value, and so we're gonna just take all the standard deviation of the the pixel values inside the radius of the ball. We're gonna take the mean of all those and then use that as our threshold. So anything with a standard deviation above the mean is going to be classified as a striped ball, and anything with a standard deviation below the mean is going to be classified as a solid ball. You can see here it doesn't work great. It gets the these two solid balls in blue, and those are solids, but everything else it classifies as stripes, which is wrong, like the orange ball, the yellow ball, and the white ball. My understanding of it, I think this occurs because of the poor lighting. It's especially obvious in the top right-hand corner with the cue ball. You can see there's like a shadow gradient on here, which is giving this ball an artificially high standard deviation. So this part of the program definitely needs some work. But it's a secondary goal, so we're just going to accept this flawed program for now. So next, we're going to talk about how we're going to map the table from these 4 corner images. And we're doing that by finding those edge markers I was talking about earlier, the circular white marks on the bumpers. So all pool tables have them. They're spaced set distances apart. Most tables, they're circles. They're really high contrast, and so that makes it really easy to find them using the circle finding algorithms in MATLAB. So this is just a first run through of finding these edges. You can see it does really well. Found almost all of them in the image with a few false detections, which we'll get rid of. So wasn't in that previous picture, but sometimes the number display on the ball gets picked up as one of these edge markers, so we don't want that, and we don't want those cluster of false detections like in the previous slide. So what we do is we just throw out any found edge markers that are too close to any of the already found balls, and then we also take edge markers that are too close to each other and just throw out the whole group. So this is a cleaned up version. You can see all the false detections are gone, but all of the true edge markers are still there. So now we need to identify these. So as you could see earlier in the slides, the edge markers would either be in one of 2 groups. Both of these groups are going to be collinear within each other. So that's what we do, is we take the centers of the edge markers and we group them based on how linear they are with all of the other edge markers. And so that gives us 2 linear groups. And then we need to determine which group is on the long edge of the table and which group's on the short edge. So what we do there is take just the group with the most, with the largest contents, that's going to be the one on the long edge. The group with the smaller contents is the one on the short edge. And then we can further identify these edge markers because we know what corner we start at. So we know the edge marker farthest away from the pocket, we know where that is globally on a pool table, and the one closest to the pocket, we know where that is. So we can just match these with these global global locations for these markers. This is this example of the grouped edges. You can see the long group is in green, the short group's in red. So now we want to project the balls that we find in these corner images onto the top-down view of the table, so we have a proper mapping of the entire table. So we're going to create a synthetic image, just that's going to have the key features of the table, and then we're going to mark where the balls are on that. To do that, we're going to use the fit geotransform function in MATLAB. So this function needs 4 points from a source image matched to 4 points on a destination image. So we're going to use the located edges. So we have where the edges should be globally, and we have where we found them in each image. Using that, we can find a projective transform that maps the corner image to the top-down image, and we can apply this to the ball centers. This is an example of the synthetic image we created. You can see all the edge markers are marked here, as well as the corners of the playing table. This is an example of a populated digital table. So each instance of color is balls that were projected onto this top-down view from a different corner. So the red are all balls found that were found in the bottom right corner of the table, and from that picture we took from there. Green, same thing, top right. So how well does this work? So over 20 test images, there were 105 balls in the images. We found 92 of them, so 8%, 87.76% success, which isn't the best. That could also be improved on. And then the classification, as we discussed earlier, does not work very well. So it very underrepresented the solids while overrepresented the stripes. It should be noted that a stripe or a solid was never mistaken for our stripe was never mistaken for a solid. So there is hope there, in that this could be a plausible way to determine the classification of the balls. So how did the mapping work? So 5 out of 5 image sets were successful. So an image set is just the group of 4 pictures, one from each corner of the table. So the edges were always found and identified correctly. In every picture, we never found too few edges or misidentified any edges. The only problem with the table mapping is that the ball location is not very accurate for balls that are towards the center of the table. And we'll talk about that later. I also ran this algorithm on a non-traditional pool table, one with blue felt and diamond edge markers on a very shiny surface on the edge, and it was very poor results. None of the edge markers were detected because we were looking for circles instead of diamonds, and a few fewer balls were detected on occasion, but mostly it worked better, or as good if not better, than the ball finding in the traditional table. So I said earlier that as balls get closer to the center, we're less certain about their location, and that's because we're using just these edge markers to create this transformation. So we have a lot of information about the corner of the image, but as we stray from our known information out into the center, like this purple striped ball, we're farther away from the things that we know to be true. And then so the projection fails, and you can see as we move away from the pocket, the image is getting stretched more and more with this projection transform. And the way I deal with that is these balls, we assume they're going to be closer in another corner's image. So if they're past the known locations, like past this bounding box that I'm outlining with the mouse, we just don't plot them in the top-down view, hoping that we'll get them in another image closer to the true points. So there's still a bunch of room for improvement in this algorithm, and there are a couple pretty easy fixes we could try first. So first we could increase the picture size. Just for the speed of my tests, I was using only 600 by roughly 800 pixel images. So, I mean, using like a megapixel image would probably help with everything. So there'd be more pixels to average over for the standard deviation. We'd have higher accuracy of the center of the balls. I was using a really poorly lit pool table because I wanted to. It was the only one I had, but also I thought it'd be pretty realistic of having just being able to use any pool table that you come across, use this algorithm on. You're not going to have control of the lighting all the time. The classification algorithm, as I've said before, is not very accurate, so that, I mean, we could just throw out the standard deviation method and try a completely new method. Something else we could do is require the user to just take as many of those, or take the pictures in such a way that as many of those edge markers are in it as possible. That would improve the width of that like bounding box of accuracy that we defined. And then finally, we could really accurately locate the balls if we could uniquely identify them. So in a given corner, a ball that's far away is going to be projected even farther away in that corner from that corner. But then that's going to happen on all of the corners. So if we uniquely identify the balls, locations from multiple corners are going to be projected past each other. If we knew the specific identities of the balls, we could ray trace their projections. And the intersection from projections from separate corners would be the true location of the ball. All right, and that's what I had started for a pool table recognition algorithm. Thank you for listening.